This is problem 3-179E. It's on page 181. Figure P3-179 illustrates a type of engineering chain used for conveyor applications. All components are made from AIS I-1040 cold drawn steel. Evaluate the allowable tensile force repeated on the chain with respect to shear of the pin, bearing of the pin on the side plates, and tension in the side plates. Now, as we analyze these, I'll go through and describe what they are in a little more detail. We're in a bit of a hurry here for time. So the material suggests, when we look it up, the ultimate strength will be 97 KSI, and the yield strength is 82 KSI. So there's some material properties that we will need. And let's just jump into it for part A. We're supposed to analyze pin shear. So if you look at the figure, you can see as the link plates pull on the pin, they could shear the pin. Okay. All right, so the area available for shear is pi d squared over 4. And I'm looking at this thinking I may have, no. I was thinking I may have made another mistake because the pin does go through all the way through a link. But there's nothing on the outside of the pins holding it, so only the inside area would shear. So this analysis should be sound. Anyway, calculating that shear area, it's just a circle, so it's pi over 4. 5/8 of an inch basically squared. That's the diameter. And so this comes out to about 0.3117 square inches. Now this is just one side of the pin. If it's a 5/8 pin, then that's the area if you were to cut the pin and look at it. So this is just one pin side. Okay. Now the design stress, the design shear stress that we'll allow is the yield strength over 8. We've referenced the table several times, so in the interest of time we won't go back to it. But basically this is just the allowable shear stress for a repeated type load. Okay, so it's just another thing in the table. So if you take the 82 over 8, because it's 82 yield strength KSI, you get 10.25 KSI as the allowable stress. So to calculate how much force these can take, well, the shear multiplied by 2 times the shear area. Why 2? Well, notice that we're talking about the force in the chain, right? There's 2 link plates on each side. So if you imagine you could cut the bolt at 2 different places where load's being applied in shear. Does that make sense? Clear? So that's why there's 2 times that area. So anyway, we've got all the numbers here. We've got the specification, we have the area. Plug all that into your calculator, you'll find it's 6.39 thousand pounds, so kips. So there's the answer from the first part, so we'll just tabulate them up here. Part A, the maximum force in the chain would be 6.39 kilopounds, or 1,000 pounds. Any questions on that part? Went through it pretty fast. So basically that's the maximum load that the chains could support as far as shearing in the pin is concerned. So we're going to calculate the loading that could be subjected to the chain link if the pin were to fail instead in bearings. So the design bearing stress, now where do we get this? We haven't talked about this, and this is a detail we need to go to and look at. Turn to page 151 and look at equation 3-22. Now the subscript B is used for bearing, the subscript DB is used for design bearing or bearing design. And basically the specification here from equation 3-22, the recommendation is that 90% of the yield strength could be used. Well, what kind of failure are we talking about? I mean, in part A, it was pretty obvious, right? Here's the pin, you've got a link here, you've got another link here, and you're applying force, and you might shear the pin, right? That's why there were 2 of them. But what are we talking about here? Well, let's change this and realize that now, zoom in on one side of it basically. There's a link plate like this, and I will draw it in section. And you realize that we're talking about a hole in a plate and a pin, right? So there is area, let me change color, on the pin surface where force is applied. Does that make sense? So it's not all the way around, obviously. It's just half the way around. There's force applied to it. And that force on the surface, like in the Glasgow Tower, could cause the surface to actually move, to deform, right? And so the recommendation we have here is that only 90% of the yield strength be used to calculate how much stress could be applied to the surface. And my drawing's not very good really. I'd rather have it like this so that you see the areas wrapping around 180 degrees like this to hold onto that pin and push on the surface. Okay. All right, so continuing this, since the yield strength was 82 KSI, I'll just write it over here, we have the space. This comes out to 73.8 KSI. Now, why am I using a sigma here and I used a tau before? What's the difference between these two things? Why was the tau used? That little funny looking T thing. The reason we use tau is because there we're talking about shear. Did you notice that the area we were talking about was an area of the pin like this, and the link plate would shear past it, right? So it's kind of like a scissors motion. Okay, so when the direction of the load lies along the surface, in the same direction of the surface, if you will, then that's a shear. In this case, the load is normal to the surface. Does that make sense? It's applied to the surface normal. And so we're talking about what's called a normal stress. So anytime you see a sigma, you know we're talking about a particular direction of the load relative to the surface that would fail. Okay? Same thing with the tau, but they're opposites of each other. Okay. Now, another note in that equation, page 151, if you turned away from it, go back, please. Actually, not that page, one page back. Page 149, equation 321. One thing that's recommended is when you have a pin in a hole like this, if the pin fits fairly loose in the hole, let me exaggerate the hole, then there's just one point of contact, and then we have Hertzian stress. Okay, but that's not what we're talking about here, because ideally we would have very close fitting, and so the pin and the hole will have contact at more than just a point. In that case, it's as if there's pressure applied to the pin. Now, the force that's actually being applied as an integral of all this pressure, that force has only one direction, right, like this. So it's just a component of the pressure over here. It's a larger component here. Here it's almost all of it, okay? So how do you deal with that? Well, the way you deal with it is instead of considering the area all the way around 180 degrees, you take the projected area. And this is fairly common. You'll see this in other classes. So let me expand this. Let me draw the pin like this. And here's the surface where we're applying force normal to the surface. And we assume this is lubricated, so that's the only way we could apply force. In that case, all we're going to do is take the projected, I should go through that dotted line I drew. We're going to take the projected area because that's equivalent to neglecting all the force components that are not in the same direction, or all the pressure components not in the same direction as a force. Does that make sense? So that's why when we talk about bearing design with a round pin like this, we will calculate the bearing area as the diameter of the pin times the length. Okay? I know that's not the area of that surface, but that's the projected area and accounts for the varying pressure direction. Okay? So anyway, the projected area is 0.63 inches. That's the diameter multiplied by the length of the pin. The pin's, now you have to be careful here. The length of the pin goes all the way across the length, but the area we're interested in is only in a certain area of the mechanism, right? It's in the width of that side plate. Does that make sense? So that's the length where we have area and we're actually applying a surface force. I forgot my inch there. Anyway, so that area, that bearing area is, let's see, here it is, 0.2394 square inches. That's for one side, but we have two sides taking the total load, just like we did before. And so the amount of force that we can apply so that the pin doesn't fail in the surface is the bearing stress, the design stress, multiplied by 2 times the bearing area. Again, because we have two areas of the pin that are taking this surface force. So it's like the length is twice as much. Okay. Anyway, the stress is here, 73.8 KSI. The area is here. Plug it all into your calculator. This comes out to about 35.3 kips. Let's jot that down up here. F max equals 35.3 kips. So at this point, which would fail first? Would the links shear or would their surface deform? Obviously they shear, right? It takes a much lower force to shear the pin off than to deflect the surface. Does that make sense? So far, the surface is not the failure mode. It's shearing of the pin that's the failure mode. But there's another way that these pins could fail, and that's part C. Okay, if you look at the problem statement, it says, what about tension in the side plates? Well, these side plates are being pulled, right? There's force in the plates as well, so that's another place that this chain could fail. Now, there's more than just this, but for our purposes in learning the class, these are the three primary ways we've talked about, or three primary types of stresses we've talked about in this chapter. Now, we have to consider what's going on here, because basically from the side, what this is a member with a hole in it. So we're really not interested in fracture here, we're interested in fracture here, right? Because there's going to be stress concentration due to that hole. So now we have another stress concentration type of problem where the, let me put some dimensions on here. The width is 1.5 inches. The thickness of the plate is 0.38 inches. We've already used that fact. And then the diameter of the hole is just the diameter of the bolt or the pin that's going through the hole, that 5/8 inch pin. Okay, you guys with me so far? All right, so we should be able to come up with a stress concentration factor based around this hole. But to do that, we'll have to go to the back of the book and look up the stress concentration factors. What kind of loading do we have? Which figure should we look at? Well, look at page 727, and you'll see a picture that looks a lot like what we have. So here's the basic geometry that matches our loading situation or our design situation. What are we talking about here? Is this direct tension? Is this tension applied through a pin in the hole, or is this a bending? Which do you think we should look at? Curve A, curve B, or curve C, and why? I have one vote for B. Anyone agree or disagree? Say something different? Well, it's obviously not C, right? We're not talking about a plate where we're trying to bend it, right? We're just applying force. So yeah, definitely B, right? Because it's a pin applying force to a hole, right? So it's curve B that we're interested in. And so what we'll have to do is use the equations at the center, and basically it says that the nominal stress is equal to the force being applied divided by the width less the hole size, the hole diameter, times T. So what is this doing? Well, this is just calculating the area in this section, right? You don't have material in the hole, so if you take the total width, subtract off that length, and then multiply by the thickness, now you've got the area down here and the area here. Sorry, my diagram's getting messy, but do you guys see what I'm saying? So that area would look something like this, where this dimension is the width, this dimension is the thickness, and this dimension is the diameter of the pin. All right, so let's get rid of all the mess here, because I don't think we need it anymore. Oh, I needed those dimensions. Oh well. On the x-axis, we need the diameter of the pin, I think I can remember them, divided by the width of the link. Okay, now when we take that ratio, we get 0.42. So that's where we're at on the x-axis. And with curve B, what stress concentration factor, KT, do you think we should calculate or read off? So 0.42 on the x-axis, go up to curve B, about what KT do you get? How much? 3. About 3. Anyone agree with that? Does everybody see how you get 3? If you see how to get 3, turn around and show the person behind you. I'll make sure everyone can see it. So on the x-axis, 0.42, this is 0.442, this is 0.45, so this is about half. Oh, I see. No, 0.42. So is that the over-W ratio? Everybody on the front row see how to get it? Anyone not see it? Okay, if you see how to get it, turn around, make sure the person behind you can get it. If they can get it, fine, let them turn around and go to these. Okay? I'll give you about a minute to make sure that this is clear. My best guess. Okay, so I guess I was a bit arrogant and I said 2.95. Is that exactly right? If you said 3, is that wrong? No, 3 is fine. Okay, so I said there's our nominal, now, or our KT. Now, one thing to note here is that the area, let's calculate this. This is basically the area of that cross section that I showed you earlier. You can calculate this, so I'm not going to bother with it. I'll just make a note that this is equal to, when I did that I got 0.3306 square inches, but we have to be careful again because we've got 2 link plates, right? So there's this area on both sides to consider, so we have to be careful about that. Not only that, but this nominal stress, we'll have to multiply it by the stress concentration factor. We have to work all that into this. Okay, so let's just continue. The design stress, here I'm going to use the ultimate strength over 8. Why? Well, look back at the table we've referenced many times, and you'll see why I chose it. I'm running out of time, so I don't have time to go through that. But you'll see why that was selected. And so anyway, that's 97 KSI over 8, which comes out to 12.125 KSI. And then the design stress is also equal to force over 2A, because again we have 2 link plates, one on each side. And so, you know what? I don't think I incorporated the stress concentration factor in here. I've got a mistake. I'll have to fix it. I'll show you what I did, and then I'll let you think about what I should have done. Times 0.3306 square inches, and then the design stress, I just plugged in 12.125 KSI, and I got 8.0 kips. However, what should I have done? Well, I should have taken the 2.95, that should multiply the actual stress that we're getting, so I've got to work that into the equation. Basically, if you take this number, you divide it by 2.95, that would be the maximum force. So it looks like the link plates are going to be the, excuse me, the place where this chain would fail. Is that a good design? I don't know that it really matters where the things fail, because if the pin fails or if the link plates fail, you're going to replace at least that link in a chain this size. Not the whole thing probably, but at least that section. Okay? All right, thank you for your patience.